So far, we have discussed chemistry and chemical reactions and calculations based on solid substances and liquid reactions or solution reactions, but we haven't discussed the gaseous state yet. Depending on the pressure and the temperature of your substance, it could exist in one of the three physical states: solid, liquid, or gas. So at low temperatures, it will be in the solid phase, where the molecules or the atoms are restricted to very specific positions and cannot move around with respect to each other. When you heat them up, it will have a little bit higher kinetic energy and it will transform into a liquid phase. And if you heat it further, it's gonna be moving completely independent with respect to each other in a gaseous phase. And this is the phase diagram that correlates the different phases or the different states of substances depending on the pressure and temperature. Each line of these represent the transformation or the conversion from one state to the other. So that line is the melting, freezing transformation depending on the direction. And it basically defines the melting point of the substance. This line is the condensation, vaporization between liquid and gas phases, or it defines the boiling point of the substance. And this line is the deposition, sublimation, transformation between the solid and the gas phase directly. It defines the sublimation point, and you can clearly see that each substance is going to have several boiling point or melting point or sublimation point depending on the pressure. So water, for example, is going to boil at 100 degrees Celsius only at 1 atmosphere. But if the external pressure is different than this, the boiling point of the substance is going to be different. So gaseous state is quite different than the solid and liquid states, and it has quite different properties. For example, a gas will expand to fill the volume of any container it occupies, and it always have much lower densities compared to solids and liquids. The densities are actually quite variable depending on the conditions, like depending on the temperature and the pressure of the sample, and they readily mix with each other, and they drastically change volume by changing conditions like temperature and pressure. So their properties should be described very differently than solids and liquids. In chemistry, as we learned before, we usually are interested in the quantity of our reactants or products in terms of number of moles. And if these substances like reactants or products are solids or liquids, we can always quantify the number of moles by measuring mass. In case of gaseous substances, it's extremely difficult to measure masses. In this case, would usually correlate the quantity of our gaseous substance in terms of volume. So that's the first relationship, how the volume of a gaseous sample correlates to the quantity of the gas in terms of number of moles. And as we said, properties of any gaseous sample is gonna change significantly based on the conditions. So the volume of any gaseous sample is not constant. It actually significantly depends on the temperature and the pressure of the sample. So we need to study what's the relationship between the volume of the sample and the temperature and pressure. And those three relationships, the relationship between the quantity of the gaseous sample with its volume, and the relationship between the volume and temperature, and the volume and pressure, are the three gas laws that are later gonna get combined into the ideal gas law. And we're gonna discuss those step by step. I'd like to get started with Avogadro's law, which is the relationship between volume and number of moles. Because as we said, in chemistry, we're interested in the quantity of the gaseous sample in moles, and we usually want to quantify this into a measurable amount that we can measure. So in case of gases, the measurable property that we can measure for the gas is the volume of the gaseous sample. Experimentally, this relationship was determined, and it was found to be directly proportional. The volume of a gaseous sample is directly proportional to the number of moles, which means the volume of the sample equals a constant times the number of moles. This is correct provided that your sample is at constant temperature and constant pressure. So when you do a reaction that transforms 3 moles of a reactant plus 1 mole of a second reactant, a total of 4 moles, and produces only 2 moles of a product, 1 mole of any gas is gonna occupy the same volume. So 4 moles in the reactants are gonna occupy 4 equivalents of volumes. Once they react to produce only 2 moles of products, they will only occupy 2 volume equivalents of gases, which means the volume is gonna get reduced in half in the same way as the number of moles got reduced in half due to the reaction. The second property of interest in terms of gaseous samples is pressure. And pressure in physics is defined as the effective force per unit area. And for the atmospheric pressure, it's basically the weight of the column of air per unit area throughout the atmosphere. And that's why when we define the units for pressure, the most common unit is 1 atmosphere, which is basically the pressure of a column of air throughout the height of the whole atmosphere. But the SI unit for pressure is 1 Pascal, which is basically the SI unit for force, Newton, divided by the SI unit for area, meter square. And if you analyze these units, it's going to equal kilogram per meter times second square. So the interconversion between these two commonly used units is that 1 atmosphere equals 101,325 pascals, or 101.3 kilopascals. One other unit commonly used is 1 bar, which is 10 to the power 5 pascals. So that makes the 1 atmosphere equal 1.013 bars. Also, a common unit used in the United States is the pound per square inch, which is basically the ratio between the force per the common unit for area, which is square inch, and it's abbreviated to be PSI. In 1 atmosphere is going to be 14.7 PSIs. Another commonly used unit is millimeter mercury, or sometimes also known as torrs, because the effect or the weight of 1 atmosphere is going to be able to push a column of mercury with the height of 760 millimeter. So 1 atmosphere is actually equivalent to the weight of 760 millimeter of mercury. Finally, that height in inches is 29.92 inches. So 1 atmosphere is going to equal the weight of a column of mercury with the height of 29.92 inches. Okay, that takes us to defining the relationship between the volume of a gaseous sample and its pressure. So if you confine a gaseous sample in a container, a certain initial volume, and you increase the pressure, what do you expect? Makes sense to expect that once you increase the pressure, the volume is going to decrease, and vice versa. Once you decrease the volume, pressure is going to increase. And that means that pressure is inversely proportional to volume for any gaseous sample, or mathematically, volume of the sample is proportional to 1 over pressure, or volume if any gaseous sample is going to equal a constant divided by the pressure. If you rearrange this, it's going to mean that the product of pressure times volume is going to equal a constant. In other words, if you mathematically plot the pressure of a gaseous sample versus 1 over V, it's going to give you a straight line with a slope that equals a certain constant, right? And in terms of comparison for a certain sample between two different conditions, the pressure times volume for condition 1 is going to equal a constant, is going to equal the pressure times volume for condition 2 equals the pressure times volume for condition 3, and so on. And that last expression is very useful to calculate the pressure of a gaseous sample when you change the volume and vice versa. So if you have a helium balloon with this volume here at sea level, which corresponds to 1 atmosphere pressure, and you make it rise to a height of 6.5 kilometers up, where the pressure is gonna drop to 0.4 atmosphere, what would be the final volume? So here is the initial volume of the sample, here is the initial pressure of the sample, and here is the final, the initial pressure of the sample, and here is the final pressure of the sample, and you're looking for the final volume of the sample. We know that pressure times volume for condition 1 is going to equal pressure times volume for condition 2. So we basically need to rearrange this to solve for V2. V2 is going to equal P1 divided by P2 times V1. So it's going to equal 1 atmosphere divided by 0.4 atmosphere times V1, which was 0.55 liter, is going to increase to 1.375 liters. And that makes sense, right? Because we know that volume is inversely proportional to pressure, which means if pressure decreased, volume is going to increase. That's exactly what happened. Pressure decreased from 1 atmosphere to 0.4 atmosphere. The volume increased from 0.55 to 1.375. The last relationship here is a relationship between the volume of a gaseous sample and its temperature. So when you put a gaseous sample at low temperature and then you increase the temperature, what we experimentally see is that the gas will expand as the temperature increases. When you increase temperature, is gonna increase volume and vice versa, or mathematically volume is directly proportional to temperature, or volume equals a constant times temperature. But we have to pay attention to something really important here. Temperature here is not temperature in Celsius. If you use temperature in Celsius gets negative values. So if you use negative values for temperature, you will get negative values for volume. And that's basically physically impossible. No object can occupy a negative volume. And that was the reason why we had to invent the absolute scale for temperature, the Kelvin scale for temperature. So temperature here has to be in Kelvin, or it's actually equals a constant times the temperature in Celsius plus 273.15. So it has to be expressed in Kelvin, not in Celsius. Because again, if you plot volume versus temperature in Celsius, basically it's going to be a straight line, but it's not going to cross the origin. It's going to actually go all the way down to negative 273.15. So we had to adjust for this fact by developing the absolute temperature scale in Kelvin. And in this case, it's going to give you a straight line that crosses the origin for the plot of volume versus temperature in Kelvin. And again, for comparing a sample in two conditions, we know that V1 equals constant times T1. If you divide this by V2, it's going to equal constant times T2. So V1 divided by V2 is going to equal T1 divided by T2 if you cancel out the constants to each other. That's an important formula to compare one sample in two different conditions, or to calculate the volume of a sample when the temperature changes. So to just summarize these experimentally determined relationships for any gaseous sample, what we quantify the gas with is volume, and we needed to correlate volume of a gaseous sample to each of the other three properties: number of moles, pressure, and temperature. Volume is inversely proportional to pressure, which means when you decrease volume, pressure is going to increase. When you increase volume, the pressure is going to decrease. That's the principle for Boyle's law. For Avogadro's law, which is the relationship between the number of moles of a gaseous sample and its volume, it's very straightforward. Number of moles is directly proportional to volume. More number of moles is going to make it occupy more volume. Less number of moles is going to make it occupy less volume. And Charles' law is about the temperature relationship with volume. When you lower temperature, volume is going to decrease. When you increase temperature, sample is going to expand to larger volume. And based on these three experimentally observed laws, we can actually deduce a relationship between the temperature of a gaseous sample and its pressure. When you lower the temperature, pressure is going to decrease. When you increase the temperature, the pressure is going to increase. So pressure and temperature are directly proportional to each other. If we combine these three observations, first one is that the volume of gaseous sample is inversely proportional to pressure, and then the volume is directly proportional to temperature, and the volume is directly proportional to number of moles. You combine them, it means that the volume is proportional to number of moles times temperature divided by pressure, which means the volume equals the constant times the product of these three properties. That constant, the proportionality constant in this case, is called the universal gas constant, R. So that gives us the ideal gas law that correlates the four parameters for any gaseous sample: pressure, volume, number of moles, and temperature. Proportionality constant in this case is called the universal gas constant, R. And we can calculate the value of this constant by measuring the volume of a gaseous sample at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, usually abbreviated with STP. If you measure 1 mole of any gaseous sample, it's going to occupy exactly 22.414 liter. So we can use these observations to calculate R, because R is going to equal P times V divided by N times T. So we will take the pressure, which is 1 atmosphere, multiply times the volume, which is 22.414 liter, divided by number of moles, which is 1 mole times the temperature in Kelvin, which is going to be 273.15 Kelvin. When you calculate these numbers, it's going to give you 0.08205 liter atmosphere mole degree. This is the value for the universal gas constant. We can always express this in different units. So it will take the value of 8.314 joule per mole Kelvin, or 62.37 liter torr per mole Kelvin. It's basically based on what units you use for volume, pressure, moles, and temperature. Which one of these three values you will use is going to depend on what units you use for each one of these parameters. What units you use for pressure. So if it's atmosphere, so you have to use the value that has atmosphere in it. If it's in torr, it's better to use the value with torr in it. If it's in actually liter times atmosphere equals joule. So if it's in joules, you have to use the one with joules in it. A second iteration of the ideal gas law is very useful to calculate molar mass of a gas. Because if you consider the number of moles of any gaseous sample, is basically equals the grams of the gas divided by its molar mass. So it's the mass of the gas divided by molar mass. And from the ideal gas law, pressure is going to equal number of moles times R times T divided by V. So if we substitute for the number of moles from this expression right here, is going to equal mass divided by molar mass times RT over V. So it's basically equals the mass times RT divided by V times the molar mass. But we know that density is mass by volume. So the mass divided by volume can be substituted with density. So pressure equals density times R times T divided by molar mass, or you can rearrange this formula here to calculate molar mass. So if you calculate the density of the gaseous sample, you can easily find out the molar mass by multiplying it times RT over P.